We've been working with differentials, and so I want to go through a couple of example problems that require us to use differentials. This first one states that the radius of a circle is increased from 2 to 2.02 meters. And then we're asked to do two things: to estimate the resulting change in area and to express the estimate of the percentage, the estimate as a percentage of the circle's original area. So let's start by reminding you what differentials are. We define the differential dy as f prime of x times dx. And dy is an estimate for the change in the function. So that's great, but this example problem has real context. And so y and x are not the variables here. We're dealing with radius and area. So what we need to do is adjust our point of view. In this case, when we talk about the area of a circle, we're talking about pi r squared. Notice that r plays the role of x and a plays the role of y in this equation. So instead of dy equals f prime of x dx, we are looking for dA, which will be, we'll call it f prime of r dr. So we're going to take the derivative and multiply by the change in r. So let's get that derivative written down. dA over dr is going to be 2 pi r, and then dA would equal 2 pi r times dr. And notice from the reading, the original radius was 2, so r equals 2. And it changed to 2.02, meaning that dr is 0.02. So if we're going to estimate the change in the resulting area, in other words, if we're going to compute dA, we have to do dA equals 2 pi times the original 2 times the dr, which was 0.02. And that calculation will be the estimate for the resulting change in area. That'll be our dA. So when you crank this out in the calculator, if you're going to write it in terms of pi, you get 0.08 pi. That decimal is approximately 0.2513. And this is the answer to letter A, to estimate the resulting change in area. dA is an estimate for the change in area. So the area increased by about 0.08 pi when we increase the radius by 0.02. Now letter B asks us to estimate that change as a percentage of the original area. So that means we got to compute the original area. Well, the original area is easy to compute. We just use this formula with the 2 in there. So that's 4 pi. So the original area is 4 pi. And not sure why I switched to blue there. Actually, I know why. I was going to put my letters in blue, and then I kept writing. So what we want to do is write down 0.08 pi over 4 pi, and then we'll multiply that by 100 to get the percentage. And that's going to work out to be, that's 2%. So we did a 2% increase in the area. Let's take a look at another example and see if we can get a better handle on these differentials. In this problem, we're asked to estimate the volume of material in a cylindrical shell with a height of 30 inches, a radius of 6 inches, and a shell thickness of 0.05. So be careful with this problem, because we're not actually asking how much stuff will fit inside of this cylinder. We're asking about how much material it takes to make the cylinder. So I'm going to just kind of exaggerate this picture a little bit just at the top here. So if we have the top of the cylinder here, there's a thickness to this thing. And what we're asking is how much material it takes to make it, right? So you can't really see the thickness from the outside because it's covered up, but you can see it at the top, right? That there's this thickness here that we're worried about. And we're going to estimate that by pretending that we have the inside shell, right, which is razor thin, and we change the radius to the outside shell. This is a terrible picture, but we're going to estimate that change in the volume of the entire cylinder in order to estimate the shell thickness, or the material that we need to build the shell. Let me show you what I mean. If we just take this in terms of its geometric properties, the volume of a cylinder is pi r squared times h. In this equation, the height is actually a constant. It's not changing. Only the radius is changing. So I can rewrite this equation as 30 pi r squared. And if I want to estimate the change in volume, I'll do a differential. And that differential would be dV equals the derivative here, which is 60 pi r times the dr. And we're just going to plug in the radius of 6 and the change in the radius, which is 0.5, and we'll crank this thing out. So essentially what we need to compute is 60 times pi times 6 times 0.5. And I can actually do a lot of that math in my head here. Half of 6 is 3. 3 times 60 is 180. So we're talking about 180 pi. And if you want the decimal approximation, that's approximately equal to 5.65. Nope, not 5 point. Can't even read my own calculator here. That's 565.5. And that we're talking about cubic inches here. So both of these are measured in cubic inches. And that will be our answer for this one. The strategy on these problems is to turn the written statement into a formula so that we can take the derivative and then multiply by the dx, whichever variable is playing that role, so that we can then plug numbers in and get the estimate. It all boils down to that same differential formula that we learned, which is dy equals f prime of x, the derivative, times dx. Hopefully these two helped. And again, you know where to find me if you have any questions. Take care.